Hello, everyone, and welcome to the latest best practice webcast. This one's on Informix query performance tuning. Thank you for joining. We're about to start. So my name is Mike Walker from Advanced Data Tools, and today we're going to be talking about query tuning. And just before we start, I did want to let you all know that the webcast is being recorded, and we'll be posting the replay, the recording, and the slides on our website in just a few days. Just a reminder to please keep your line on mute so we can keep the background noise down to a minimum. And if you have any questions, I'll get to those at the end. But go ahead and submit them using the chat button at the upper right side of the page. So, performance tuning basics. So the majority of this webcast is going to focus on how to find long-running queries, then tuning them using the explain plans and directives. If we have time, because that's going to take most of the hour, we'll talk about the monitoring the Bufferpool usage, looking at the tables that might be using, doing a lot of I/O, and how to check if your statistics are up to date. Okay, jumping right in, how do you tell on a system what's running? So all of the Informix sessions that are out there, how do you see what's doing anything? You're probably familiar with the onstat -u command, which just lists all those sessions. In that output, there's a flags column, and the first position of those flags can tell you what the session is doing. Often you'll see a Y. The Y just means that the session is waiting on something. It's often waiting on the network. Maybe something as simple as a DB access session where it's waiting at the next, someone's pressed next, or a session is completed, but the connection is still open to the database. If there's anything else in that first position, it normally indicates that the thread is running or it's waiting on something other than another query to come along. You may see a B means it's waiting for a buffer, an L means it's waiting for a lock. All of these kind of things you're interested in. So if you run onstat -u and then filter out anything that is not beginning with a Y, where that first position of the flags is not a Y, probably shows you sessions that are active. So here's a sample of onstat -u, and the lines that are highlighted show the sessions where that first position, in this case, is just a hyphen. So these are the sessions that I'm going to want to dig into a little bit further. So once I found some sessions, I can use onstat -g NTT to show me when that session was started. That's when it was first connected to the database. And then looking at the last column of the output, it shows a time. And that shows me the time the last query was submitted to the database. So if by using onstat -u to find out what is active, what is actually running, and then comparing that to the output of onstat -g NTT, I can find out what SQL is running now and how long it's been running, because I just look at the time that it was last submitted. I know it's active, and the difference between the time it was last submitted and the current time is how long it's been running. So I can combine those two bits of information together and start looking at the sessions that might be running for a long time. So here I'm showing the sessions, and it's repeated every second, and I'm looking at the output of onstat -g NTT. I'm taking those times to see when a session connected and the last time it ran, and then the current time. And then I show the reads, the writes, the locks, and the flags. So looking at some actual output, what I'll see here, remember I'm running this every second or so, I will see these sessions here, the times are updating, meaning that new SQL has been submitted to the database. The ones highlighted in red, these sessions, these have been waiting for a while or executing for a while. I know they're executing because the first position of the flag is not Y, and I can see that the last time SQL was submitted was, in this case, the first one was 20 minutes ago, and the other one was 10 minutes ago, where this is the current time. So these are the ones I might want to take a look at and see why are these taking so long to run. So once I find a session to look at that might be running for a while, I can take a closer look at it by seeing actually what it's running by running the onstat-g SQL, supply it the session ID, and then get that to repeat every second. So when you do that, it won't take long to see if the SQL is changing and whether you're seeing a whole bunch of different types of SQL running, just different commands, or what you may often see is the same SQL running again and again, sometimes with different literal values. Perhaps it's embedded inside a loop. If you see one statement that just keeps coming up frequently, even though there might be other statements in between, but you see this one in the output and you're checking it, let's say, every second, if you see it keep coming up, chances are that this statement is being repeated so much and it's running slower than the others. Otherwise, it wouldn't show itself as being a common SQL. And that might be what you want to start with. Now, that's mainly for an OLTP system where you're expecting SQLs to run through pretty quickly. You can do the same thing like on a reporting system. You can use the output of onstat-u and onstat-g NTT together to find out how long any SQL's been running. And then maybe if it exceeds a certain threshold, then write it out to a file. And then you can take a look at it. You may also be familiar with Informix's SQL trace feature, which is very powerful and another way to find out the long-running SQLs on the system. I'm not going to cover that here because it's being covered in other webcasts, and there's quite a bit on the web there about it. Okay, so now we found some SQL that's running a bit slow. Let's find out a bit more of what it's really doing by looking at the query plan. One way to do that is to turn on the dynamic explain with onmode-Y. You supply it the session ID, then a parameter 0, 1, or 2, and an optional file name of where you want the output to go. So the 0 turns off the dynamic explain if you've already set it. The 1 creates or writes out the plan and the query statistics. If you just want the plan, you use a value of 2. So once we set the onmode-Y, the dynamic explain, we'll see that listed if you just run onstat-g SES or onstat-g SQL. It will show that a particular session has dynamic explain set. So if you're using the dynamic explain, an explain file will be written out to the user's home directory, and it'll have the session ID as part of the name. The default name will be sqexplain.out, followed by the session ID. But you can override that and the directory by specifying the file name and a full path when you execute the onmode-Y. So looking at the contents of that file, the first thing we see is the query that was running, and then that's followed by the query statistics. And we'll go into these when we start going through explain plans in a little bit. Now here I see the query statistics because I supplied the 1 argument to onmode-Y. Now that's great, but some limitations by using the dynamic query plans is that it won't produce any output until the next statement runs. So if there's a long-running statement, it's taken a while to run, and you execute onmode-Y, you won't see anything in the file because it won't be triggered until the next command runs. And also, if your SQL is using a prepared statement, then again, you're not going to see too much because the query is already prepared, and which means the query plan has already been established, and it won't be written to the file. You will see the SQL listed, but not the query plan. So that might be the first step, but if you really want to dig into this, the best thing to do is to capture the SQL, just grab it from the screen of an onstat -g SES or SQL, and put it into a file. And then we can start looking at explain plan for that particular query. And we can do that by going to DB Access and surrounding the query with these statements. Start with set explain on, you run your SQL statement, and then optionally you can turn the explain off. If you don't turn explain off, it'll stay in effect for the remainder of that session. By default, the query plan will be written to the file sqexplain.out in the current directory. If you're running this from a client application, then it will be in the home directory of the user that's running the SQL. If there are multiple statements that you want to get the explain for or get the query plan for, the file sqexplain.out will just be appended to with each statement you run. It won't overwrite the file. Now you can also override the name of the file from sqexplain.out to a name you specify. And you use that with set explain file to, and then give it the name of the file you want it to write out to. So in this example, I'm doing just that. I want to explain the query plan to go to a file called slow1.exp. Then I set the explain on as usual. I run the SQL statement, and here I put it to dev null because I don't care about what it's producing at this point. I just want the query plan. And then once I've got this in the file, I'll run the statement with DB Access and a timex just to see how long it's going to take. And once this is done, I'll have a file called slow1.exp, which I can then take a look at. So here's an example of a query plan, and it begins with the query itself, some other information, and then details of how Informix optimized that query. Now, if the query is allowed to complete, and you've got explain stat equals 1 in your onConfig file, once the query is done, the explain file will then have some information on the query statistics. So this is really useful for getting a breakdown of how long each part of executing that query took. Now, if your query is doing an insert or an update, it may be something you don't actually want to run just to get the explain plan. So here you can use the avoid execute argument after set explain on. So what this will do is still get the explain plan for you, but it won't run the query. When you do execute the file, you'll see that 0 rows have been changed, and depending on the version of Informix you're using, you'll see this message that it's just warning you that avoid execute has been set. Now, because the query didn't actually get to complete, because it didn't even run, then you will not see the query statistics, because it won't have actually calculated how many rows were read, how many rows were needed, and how long each part took. So it just can't show you anything. All right, now let's start looking at how the query plan is broken down, because it can look a little intimidating at first. But it always follows the same basic format. The query plan will begin with the query, the SQL of the query actually being executed. That'll be followed by a few lines that tell you the estimated cost, how many rows it expects to return, whether temporary files were used, when the directives were in place. And then it starts with the first table that was accessed. It'll list the table name, followed by how it was accessed, whether it was an index, sequential scan, or whatever. Then, if filters were applied to that first table, those will be shown. And if an index was used to retrieve the data, the information on that index will be shown. So that's the first table hit. Then, if there's another table in your query, that will be listed, and the same thing will be shown. The name and the way the table was accessed, followed by any filters applied, and the index that was used, if one was used. After the second table, then you will see the method that the two tables were joined together. And there's different ways they'll be joined. Normally, you'll see a nested loop join, but there's also dynamic hash joins and others. And then if there's additional tables, that will be repeated after the join method of the first two tables is shown. Following all that, if there are any subqueries used, those will be shown after all the other tables have been joined. And then if query statistics is enabled and the query is allowed to complete, that will be shown at the end. So let's take a look at an actual example. So we begin with the query SQL itself. That's shown first, followed by a few lines that give the estimated cost, estimated number of rows returned, and in this case, you'll see that temporary files were needed because we had an order by on the SQL. That's followed by the first table that's accessed and how it's accessed. And we see here there was a sequential scan, so it was a full table read, read every row. But then filters were applied, so every row that was retrieved had to pass it through this filter. So we see here there's no index for table 1. We move on to table 2. We see the second table here, which is the orders table. And this time, the rows in the orders table were retrieved using an index. It shows index path. And more than that, it then goes on and shows that there was the actual index that was used to retrieve the records from the orders table. And there was no filters in the second example, or the second table. Lastly, in this output, we see the method that the two tables were joined. And here we see a nested loop join, which simply means once it reads a record from the first table, the database will then go and retrieve the rows from the second table. Then it will retrieve another row from the first table, then go and get the corresponding joining rows from the other table. This is a second example we're going to go through in some more detail. So here's the query plan. And the first thing you'll see, it's worth looking at the estimated number of rows. And if that's way off what you're expecting, then it could be that your statistics are out of date or statistics have not been run against these tables. So let's look at the important bit in the query plan of how the tables were accessed. So here we see the first table, we performed a sequential scan. So that's the customers table. And so sequential scan means read every single record in that table. For every record that is then retrieved, we're running it through a filter. In this case, we're looking where the cust type equals pref. And this filter is pulled from the where clause in your query. So it says, all right, any row I've retrieved, does it match the cust type equals pref? Now, if it does, then it will go ahead and do a read from the other table, the second table. This is the order table. And it will do an indexed read on that. So it'll look up that order or orders based on the cust ID. And we see that because we actually see the index here, and we see we're using cust ID, and then it tells us where it's getting the cust ID from. Here, it's getting the cust ID from the customer table using the cust ID obtained from the order table. Once it's found some matching rows, it will run them through the filter. So in the filter here, again, from the where clause is checking two columns, ship method and pay type. Any rows that match this will go on and be displayed, be returned by the query. If this filter eliminates a row, we'll just throw it away. We don't need it. So we read it, but then we threw it away. So let's get some counts of what's happening at each step here. And that'll help us with our tuning exercise. So we're reading every row from the customer table. We know that. So let's see how many rows are in the customer table. In this case, there are 100,000 rows. Now let's take a look at how many rows we filtered out. Remember, we had our filter of cust type equals pref. So by doing a query on here, we see we needed 25,000 rows. That meant we read 100,000 rows, but we only needed 25,000. We threw away 75,000 rows. Okay, so how many records did we end up joining to when we joined the customer to the order table? So here I'm expanding the SQL, now doing the join to the order table. and we read 250,000 rows to get that join. But we know once the query executed that we returned just over 6,000 records. Okay, so we read 250,000 records or more just to retrieve 6,000. Now here's a summary, and we can take a look of all of these reads compared to how many rows we actually needed. So when tuning this, we need to try and make the number of rows read very close to how many rows we actually need. Otherwise, we're reading a bunch of rows that we just don't need, and that takes time. Not only that, it's filling up our cache with pages from the table that we just don't need, and that will push out something else that we might need. So when tuning one query, you've got to think, well, this query may run fast enough, but let's not, or you need to think about the impact that might have to other things that are running through the cache. So using the query statistics that are produced at the end of the query plan, we can take a closer look to see where the actual time was spent. So looking here at the first table, which is the customer table, we know we were doing a sequential scan on that table. So we can see here the 100,000 records that were read, but after the filter was applied, we only ended up with 25,000 records. So we know this is a table scan, and our first thought might be, well, there's the problem. We need to use an index. But I can see here from the timing, the scan of this table only took less than half a second. So yeah, it's a sequential scan, but it's pretty quick. Let's look at the next table. So here's our read to the orders table. So here we're reading the 250,000 rows from the order table that matched the customer ID that was obtained from the first table. But we only needed 6,040. At the end of the day, after all the filters are applied, 6,000 records is what we needed. Okay, so that's a lot of reads for very few records that we actually need. But this is the important thing. We see here that 14 seconds was the time it took, over 14 seconds, to read all the records from the second table. So it's not the scan that's a problem, but the reads from the order table. So we need to take a closer look at those filters that we're applying on the second table, the order table, and see if we can include those in the index and get so that we only read from the order table the rows that we really need. So now using a new index where all I've done is added the ship method to the index. So we're still going in by cust ID, but now we can apply ship method to retrieving the records that we really need. We see a big difference in the rows scanned here. We're now, even though it says scanned, it's an index scan. That doesn't mean a table scan. So here we only retrieved 6,100 records. Earlier it was 250,000. And that is much closer to the 6,040 records we needed. And we can see that from the time, we're down to 1 second just to retrieve these rows. And this is because we only read those records that we really needed. So we didn't have to throw stuff away. Okay, sequential scans. And as I alluded to, we sometimes see a sequential scan, and the first reaction is, oh, that's the problem. And it's common just to get a whole bunch of query plans and just look to see, okay, where am I doing my table scans? And that needs to be indexed. Now, that's not necessarily the problem. So if you see a sequential scan, it may be okay. If you need most of the records from the table, then a sequential scan is probably the best way to get them. If you're using an index and you're reading a lot of rows through the index, there's a lot of overhead there because you've got to read the index, you've got to go through the tree to the leaf node, find the records you want, and then jump over to the data page to get the data. So there's a lot of overhead there, which if you're retrieving just a few records is fine. It's better than reading a lot of records. But if you do need most of that data, an index path may not be the best approach. So just an example here is if you're reading a sequential scan, you're just reading the data pages. You're just reading page after page, you're zooming through them. But if you're doing an index read, you're reading the index page, you've got to jump over the data page. And even if you're reading fewer records overall, you may end up doing more reads. One downside of a sequential scan, though, is even though it may be a little bit faster and you don't need all of those records, you've had to push records out of the cache. Those pages have had to be moved out of the cache to make room for the pages that I'm reading when doing the scan. That's something to consider. So here's an example where I'm reading the same table, the first method using an index, the first method doing a sequential scan and the second doing an index read. And we can see here we're reading more records through the sequential scan than the index, but the time using a sequential scan is much faster. It's actually doing the index read is about 50% longer. Okay, looking now at another example, we're going to step through this one and see really what it's doing. First look at this query plan. We see, just like the last one, we've got a sequential scan and followed by an index read. Okay, so let's take a closer look at this. Well, first we'll look at the query statistics to say, all right, so where is the time being spent here? What's the slow part? So I don't spend time tuning something that doesn't really need to be tuned. So taking a closer look at this, I see, okay, we're doing a scan, but it's pretty quick. It takes about a second and a half. So not a big deal. But looking at the time reading the second table, the inventory table, using an index, we can see that is where our time is being taken. In this case, it's almost 2.5 minutes to retrieve the records from the second table. All right, so let's take a closer look here. And I can see that we read, or we joined to like almost 1 million records, but we only needed 240,000. Maybe our first step would be to try and get those numbers a little bit closer. So only read the records that we really need. Okay, so zooming in a little bit on that second table, we can see it's using an index, and the query plan shows us the index that's actually being used here. All right, so let's step through each of the columns in that index, beginning with prodnum, the first column in the index. All right, so let's take a look here. The prodnum is, we do have that when we're retrieving the records from the second table, and it's getting the value of prodnum from the first table. We see that from where the join prodnum in the inventory table comes from the product table. That was the first table we hit, so that's good. Let's look at the second value. Okay, we're looking at the store. This is the second column in the index, so that's good. And we've got a literal value. Okay, moving on to the next value. Here we're using the year num. Okay, so that's good. It's in the index, but what we can see is it's not the next value in the index. Year num is separated from the other two values by this other column, week number. Now, we're not using week number, or we haven't specified a week number. We want to retrieve everything for the year. So in order to get to the year num, we've still got to read all the index pages with all the different values of week number. Okay, so we read those just to get to the year num and then find out, well, this isn't the 2016 I'm looking for. So again, it's good that it's in the index, but bad because year num should be further up in the index, so it can be used as a filter earlier on. And that's where we see the key first. Now, the quantity was not in the index, but it is in the query, so it's applied as a filter. And here, we're looking where quantity is greater than 0. In this particular case, we had a lot of records where the quantity was 0. So those records were read, and then they were discarded. Now, in order to find out the value of quantity to see if it matched the filter or not, we had to make a jump from the index page over to the data page, read the record just to get the quantity, and then say, okay, is it greater than 0? If it is, great. If it isn't, we did all that reading for nothing. So I changed this index. So we brought year num closer to earlier in the index. So now we can use it for drilling down for the particular year we wanted, 2016. We've added quantities to the index. Now, if you notice, the filter had a inequality operator. So it had to do a scan of the index pages, but the big thing is we didn't need to do a jump to the data page. So we've got it right there. Now, the week number, I've included that in the index, not because we're using it for filtering records, but in the original query, it was included in the select statement. It was one of the columns that we needed. By including it here, even though it's not a filter, for every record that matches our other conditions, we have the week number right there in the index. We don't need to jump over to the data page to obtain the week number. Now, this gives us a key-only scan. Key-only scans mean I've been able to satisfy everything I need from this table from the index. I haven't had to go to the data pages. And by doing that, we can really speed up queries. So looking at the query plan now, we see there is no filter anymore because we've moved quantity into the index. And we see it's a key-only scan, and we see all the conditions here. So this is looking good. Now let's look at the query statistics to see if it actually helped at all. So yes, it did. What we see is that the rows that we read were all the rows that we needed. So we didn't, in the case of the second table, we did not need to go in to, we did not have to read any records that we then didn't need. And what we can see is that second part of the table, which was over 2 minutes, almost 2.5 minutes, is now less than a second. So this query is going to run much faster. It used to be, the whole thing used to be 2.5 minutes, now it's 2.5 seconds. Okay, correlated subqueries. If you're using correlated subqueries, these can really slow queries down. An example of a correlated subquery is on the left here, where we've got a subquery, and within the subquery, we're referencing a table outside of the subquery. So we're referencing the first table, the master table, if you like. So this join here makes this a correlated subquery. Why is this bad? Well, it means that this subquery is executed every time we read a record from this first table. So in this case, the customer table. So if that subquery performs poorly, it is really going to add a lot of time to the overall execution. So often, if you have an exists with a subquery that's a correlated subquery, you can sometimes rewrite those with a join or by using an in. And let's take a closer look at a correlated subquery and see what the query plan looks like. So here we're using a not exists. And inside the subquery, we've got a join. Here we're reading from the customer table, but we're joining to the ST table. Looking at the query plan, we'll see now a subquery section. And here we can see, wow, that every time it runs that subquery, we're doing a sequential scan. If that's a large table, that's going to have quite an impact. And it shows in the filters, shows the join there. So that subquery, that scan is going to be run for every row retrieved from the first table. Looking closer at the query statistics, we can see how long or what sort of cost that subquery is having. So we see here that the overall execution time is 4 minutes, 5 seconds shown here. And the time spent just doing the subquery is the majority of that, 4 minutes and 4 seconds. And then it doesn't just show the time taken for one execution, it shows it's a cumulative time, so it'll add it up for all the times it's taken for each execution. So rewriting this correlated subquery and changing the exists or not exist to a not in this example, we only need to do the subquery one time. So instead of using exist saying, hey, is it in this table for each record we retrieve, we now run the query one time, and it will put in a list of cus keys, in this case, in temporary space, and just check against that. So that subquery will run just the once. And see the difference that makes by looking at the query statistics. And we can see here what was a long time is now just a fraction of a second, because it just had to run it the one time. So this used to take over 4 minutes. Now the overall runtime is 2 seconds, or less than that. There are times where a correlated subquery is unavoidable, and other times where they can be a good thing. If you can limit the values in the subquery by joining to the main table, you can reduce the data set that's returned. And remember that the faster you can make the subquery in a correlated subquery, those benefits will compound themselves, because it'll just, each time it's run, it'll be faster. So that's looking at explain plans there and tuning a query. One of the tools that you have when you are tuning is to use optimizer directives. Now, what directives do, they tell Informix how to run the query. So unlike other databases like hints and stuff, these optimizer directives, as long as they're valid, they will not be ignored. And the nice thing is you can also say, don't do this. Do anything else, but don't do a table scan, or don't use this particular index. And they're great just for trying little things of like, I think this would be faster if we hit the tables in this order, or if we use this index. So you can try it by adding directives. You add a directive in the form of a comment. Here's some examples for select statements where you just add a comment right after the operator, select, update, whatever. And you can use the -- plus or the parentheses or the /*, and it's followed by a plus sign, which tells Informix, hey, the next thing here is a directive. So because they're comments, and the reason for that is so that you can run them in things that may not be that Informix literate, they'll just be ignored. You can use them in 4GL, but you have to prepare them. You have to prepare the statement so that it actually makes it all the way into the database and is not ignored as a comment. There are different types of directives. I'm not going to go through all of these, but I've left them here for reference. So the main ones are the access methods, the join orders, and the join methods. Let's take a look at some examples. So for the access methods, the ones I often end up using are full, which says, hey, I want to do a full scan on this table, don't use an index. Or really it's opposite, to say use an index. And here I want to say, for this particular table, access it with this index. I need to name the table and the index. And just as I said, there's negative directives. That's where you get the avoid full and avoid index, say. So avoid full says, I don't care how you get to this table, but do not scan it. Use an index, even if it's a bad index. And avoid index says, use any index except this one, because I don't like this one. Yeah, I think it's slowing things down. Let's try it with another one. The order directive says, hit the tables in this particular order that they're listed in the from clause. There's a join method, so you can, for example, force a hash join or avoid a hash join. There's directives that impact star joins, optimization goals, get the explain plan by using a directive, and directives to say, do not go to the statement cache, or do not store this statement in the cache. So looking at an example of an order directive, and here I'm showing the explain plan, I can see I have the directive in here after the select statement, and here I'm using ordered, which says hit the tables in this order. First the customer table, followed by the orders table, followed by the items table. I see a section here which tells me, yep, I used the order directive. There's no directives you gave me that I didn't follow. And we can see it worked because we hit the customer table first, followed by the orders table, followed by the items table. You can combine directives into that comment. Just list them all out. Here I've got 3 of them. I've got the ordered. I'm saying use a particular index on the customer table. I'm using the zip IX. And do not use this index, the 102-4, on the orders table. When you're using directives, it's always a good idea to confirm that they're actually being used in the explain plan. So even if you supply invalid directives, Informix will still execute the SQL. It won't complain saying, oh, no, I can't do that. But the explain plan will show you if one was followed. So in this case, it tells you that the directives were not followed, avoid index, because this 101_4 doesn't exist. So directives, why do we want to use them? Well, sometimes when we're tuning a query, we may know better. The optimized or the query plan that has been chosen may not be the best way to access the data. So we can force the engine to run the query in the way we want, because we happen to know better in this case. And I often use it just for testing different query plans. Why, this index wasn't chosen by the optimizer, why not? Let's put it in there. And they go, oh, well, that's fair enough. It was slower. But the bad thing is that when we think we may know better, we may not. The engine often makes some very good decisions, especially if the statistics are up to date, and normally chooses the best plan. And also, if we do start hard coding the particular way a query should be executed, we may not then benefit from later changes. For example, changes in the data, or changes in indexes on the table, for example, because we've now said every time do a scan of this table, and now an index may have been added that's actually a lot better. All right, so that's most of the query tuning. I want to go on now and talk about some other things that impact the performance of how fast the queries run. So the buffer pool. This is a cache. And obviously, the more times the database can pull stuff from the cache to satisfy the query, the better, because we don't need to go to disk. By keeping a close eye on that buffer pool, it'll give you an idea of maybe some problem queries, some tables that are being dominating the cache, for example. And by looking there, you may go, oh, that's that table. I don't use it very much, so why is it taking up 80% of the cache? You may be familiar with Art Hagel's calculation of the buffer turnover ratio. This is a good idea to check on your system, just to see how fast the contents of the buffer pools are being replaced each hour. So on a system where the buffer pool is maybe not sized well enough, or you've got some problem queries, you're going to see it turn over a lot. And it'll indicate then thrashing of that cache. Tables will be pulled in, just be pushed out by something else, and that'll result in higher I/O. The guideline is to go below 10 or have that buffer turnover ratio below 10, but the lower the better. If your whole database is in the cache, then you'd expect a value below 1 for the buffer turnover. Now, there's a ratio script on the IUG site together with some other ratios that are great for getting metrics on your system. I will include the calculation right here, though, for reference. It's a pretty simple calculation going against the sysmaster sysbufpool table. So this will split down or calculate the buffer turnover for each of your buffer pools in case you have more than one. So in this real example here, we've got 3 buffer pools. We've got a 2K buffer pool, a 4K buffer pool, and a 16K buffer pool. And what we see right off the bat is that our 4K buffer pool is way too high. Remember, our guideline is below 10 if possible. You know, and if it goes to 11, it's not a huge deal, but you may want to start looking at it. But 820, there's a problem right there. Now, I like to monitor the buffer turnover ratio. It's something we do as part of our support work. And we look at it, not just the current buffer turnover ratio, but the turnover ratio over time. And so we can then look for changes, especially looking for big changes. In fact, the example on the left here, the graph shows the buffer turnover ratio increasing and then jumping. Before it started increasing, the buffer turnover ratio was below 1. It was great, indicating that the important stuff in the database, the big tables that were being used, it could normally find them in the buffers, in the cache. What happened in this particular example is a lot of the queries hit one particular table, and it's doing a scan of this large table. That table used to be able to fit in the buffer pools. The moment that table exceeded, or the size of that table exceeded the size of the buffer pools, we could no longer keep it all in there. Every time there's a scan of that table, the database had to go to disk now to pull in the rest of the table that wasn't fitting into cache. It had to go to disk, bring it into the cache, and then push something else out. So we were beginning to get some turnover. And then when there's many scans against that table, our cache is just being overwritten with each sequential scan. So our buffer turnover ratio went from like 0 to about 55. You can also use the buffer turnover ratio. You can change the formula, so you can look for differences on a smaller schedule than every day. Here for a customer, we had a buffer turnover ratio that was higher than 10, and the average value was higher than 10. So we took a closer look at breaking it down every hour, and we could see that every morning, I think it was like 4 a.m. or something, the buffer turnover ratio would jump to about 45. But during the day, which is really what we cared about during the business day, the buffer ratio was below 10. It kind of averaged around 6 or so. Oops. Yeah. Okay, so how do we find out what's using the buffer pool? If we've got a buffer turnover ratio that we want to try and bring down, we can take a look at what's actually in the buffer pool, and then over time we can see what's in there frequently and then what gets pushed out. We might see a large part of the buffer pool dominated by a table for 5 minutes, and then it gets pushed out. Half an hour later, it again is dominating that buffer pool. So by checking the buffer pool and what the contents of it and what comes in and out, we can try and identify areas for improvement. Often the thought is, well, we've got high buffer turnover ratio, we should increase the size of the buffer pool. And that's valid. It will help. The bigger the buffer pool, the more stuff can fit in the cache. And you will likely end up with better performance and a lower buffer turnover. But there may be things you can do that can avoid that, especially if you've already got a lot of memory allocated to your buffer turnover. You may find that the tuning exercise will bring down the buffer turnover without increasing the size of your buffer pools. So how do we find out what's in the buffer pools? Using onstat-P will give you a summary by all of the part numbers that are in there and how many pages are in each buffer pool. So there's a section for each buffer pool, the 2K, 4K, etc. And then the total column will show how many pages are in that buffer pool of the given table or index. And then there's a total for each buffer pool. So once you've found out what are potential troublemakers, you can decide what to do. It's like, okay, so should we just simply increase the size of the buffer pool? Yep, that'll help keep more tables in the cache. Could we move certain troublemaker tables into their own buffer pool so they can turn that one over without impacting the same buffer pool that's used by most of our transactional tables, for example? And if we find tables that frequently just dominate the cache, we may be wanting to zero in on other scans of this table. A scan of a large table will just overwrite all the contents of the cache. To get a better idea, we can start looking at the table counters. So Informix keeps track of a number of metrics, a number of counters for each table. And this is in the syspt-prof table in sysmaster, which is actually a view between systab names and sysptn tab. And it will only do that if you've got the table space stat set to 1 in your on config. And these values are reset if you run onstat-c or if you restart Informix. So these are the kind of values that we'll see in there. We'll see the locks that are being requested, where there's deadlocks, and importantly, we'll see the I/O. So we'll see how many reads and writes, how many deletes, and then whether those reads or writes were satisfied from the buffers or whether they had to go to disk. We'll also see the sequential scans. So for example, if we want to find out which table or index is using, doing a lot of I/O to disk, we can run a query against syspt-prof and order it by, in this case, I did the sum of the page reads and the page writes. As I said, one of the counters that's also included is the sequential scans. So we can take a look at all of the tables that have sequential scans and maybe find out which tables have the most scans. Now, looking at the most scans on its own is not super useful because some of those tables may be tiny. If a table is very small, just a few pages, then a scan is the best way to access it rather than an index because of the overhead of jumping around when you're reading from an index. You may end up doing more reads. So when you're looking at these counters, also factor in the size of the table. As with the buffer turnover ratio, we like to keep track of all of these table counters over time, so we can see if there are changes, if a table starts being accessed more, for example. And in this case, I'm looking at the number of scans on a table. And we can see every day the number of scans, and they stay fairly even and small jumps. And then suddenly there's a big jump. If we find something like that, we may then check and ask developers, like, was there a new release or something, or is there new functionality, or did an index go away, or something like that. Or maybe a new index was added that just affected performance, and we're suddenly seeing a bunch of scans. So we can also track the table counters as we're capturing SQL. If we, in this case, we're looking at a contract table that might be a potential troublemaker, and we're monitoring those counters over time, over a few second period. So what we see is over these periods, regular periods, the number of reads is increasing. Between each monitoring cycle here, the reads have jumped by 2. What we also see is the scans have increased at the same time. So we know that for every read here, for whatever's running, it's resulting in a sequential scan. But we also see that the buffer reads are increasing while the page reads are not. This tells us that despite these scans, they're being satisfied from the cache rather than having to go to disk. And then I might run this in one window while running something else in another window, looking for queries against the contract table. So I can then identify the query, hopefully, that is resulting in the scan. Okay, before I finish up, I wanted to run through update statistics. I'm not going to go into much detail into how to update statistics. There's a lot of information out there. I'd always suggest you look at running Arcagel's DoStat scripts or the AUS auto update statistics included with Informix as a scheduled job, or you may have your own way of running statistics. But basically, the optimizer will use statistics for each table and the columns to determine the best way to process a query. If you're getting performance issues, then the first thing to look at is, are your statistics up to date? If your statistics are not, then things may be running poorly. The basic statistic, and the one I think has the biggest impact on performance, is the update statistics low, which simply keeps account of how many records are in each table. You can imagine how you're going to get poor performance if Informix thinks a table only has a few records when really it's got millions, or vice versa. Informix may well not choose the right access path for that when hitting that table. So that's updated when you run update statistics low. When you update statistics medium or high, Informix will look at the columns and how they're distributed, how common particular values are within a particular column within the table. So let's look at how fresh your stats are. So now, this is a newer thing, when statistics low is run against a table, inside to update the systables n rows column within the database, it now writes the time that those statistics were updated in a column called UST low TS, those timestamp. So an example of looking at checking this database, seeing when the stats were run, we can see this timestamp against each table. So it's worth looking at that and seeing, well, how long ago were the stats run? And we can check to see how accurate they are. So this query, obviously when this presentation is posted, you can take a closer look at this query. But here we're checking the estimated number of rows in a table by looking at the systables n rows within the database for a table and comparing that against the real-time count of rows in the table obtained from systab info. So by doing a join between these two tables and seeing how close the numbers are, you can get an idea if there's a big discrepancy. If the estimate says, oh, there's 10 rows in this table, but actually there's millions, you may want to update statistics low against that table. The last thing here is checking the dates and times that your medium and high stats are being run. So here we can look at the sysdistrib table and join it to systables and syscolumns and see the timestamp for each column. So here we can see the constructed time for each column for each table. And again, we can say, oh, wow, that was several months ago. We should probably run update statistics, or why isn't this included in our update statistics? Okay, before I take a look at the questions that I know have come in, I did want to promote our next two webcasts. Coming up on November 30th, Arcagel will be doing a webcast on best practices for schema design, and followed by Tom Beebe's webcast in December on enterprise replication. Please go ahead and register for these. You do need to register for each one separately. And recently we announced our training coming up in 2018. Our training has been very popular this year, so much so that some courses have filled. So we're now accepting applications or whatever for our training in 2018. We do performance tuning, advanced performance tuning, and that's scheduled for early February, and then Informix for database administrators. which is an introduction to Informix for people new to Informix, or a refresher. It covers a lot of stuff on how to set up a database and how to do some basic tuning, things like that. So we have upgraded our training servers. So brand new servers. We haven't changed a few things because they run so much faster. So each student has their own server to use. And those servers, you don't need to take the training at our offices in Virginia. You can take this remotely and just remote access these servers. All right, now let's, I'm going to open up to questions. If you have questions, please type them in the chat window. Hit that icon at the top there, and we'll take a look. I see we have a number here. Let me just take a look. Okay, so we had a question on using onstat -GNTT and connection pools. So a connection pool will leave the session open, but so and we see that you know, with web servers and application servers connected to the server, and we will normally see that timestamp change with new statements. But there are some occasions, one of our customers particularly, where onstat -GNTT does not show the current time. It'll be updated despite no new statements coming through. Looking at the next question here. Okay, the question, if I understand it correctly, is adding more indexes to the table. If you remember, I showed an example where we had a prod num, store num, year num, and that was the new index. If we add more indexes, then will that slow things down? Yes, it may do. The more indexes you have on a table, you're gonna, any updates, deletes, inserts that table, you're going to expect to incur additional overhead because it has to rearrange that index and you know, do things with the B trees and stuff. So yes, so you need to ask yourself, do I really need this index? And if I add this index for one particular query, do I still need the index, the other index, or should I just modify that? And one of the tricky things is when you're adding indexes and you see an existing index, you never know whether you need to drop it. Maybe that other index is just bad, or maybe it's used by something else. And maybe it's used by something else that doesn't run very often. Maybe it only runs, you know, once a week, once a month. And if you start going ahead and dropping it, then you may impact something else. So that is always a concern. There are ways to check to see how busy an index is. Using those same table counters that I showed you, you can also get counts for indexes. The trouble is you'll still see those counters incremented even if an index is seldom used. You obviously see, you know, the values changing for reads and writes and so on because that's impacted by the reads and writes of the underlying table. But you can also get an idea how busy an index is, so it can give you a clue whether you may be able to drop that index. But yeah, there's no hard and fast way, I'm afraid, to identify that. And I'm not going to apologize for my accent. Yeah, if you have any more questions, please go ahead and type them into the chat window. Okay, I'm not seeing any other questions, so I'll just finish up with a little bit about our company and how we do remote support and training and consulting. And finally, thank you. Thank you very much for attending this webcast, and a reminder that we will hope to post this in over the next few days. Thank you very much.